we can begin with today's session. So, Mr. Ankur Mishra is currently the chairman of the Department of Astronomy and Astrophysics at Spaceonova, and he is an engineer from IISP. He holds his expertise in machine learning, big data handling, solar astronomy research, and he has also written a research paper on economics and government policies in big data handling. And his interests also include a bit about black holes, and he has been to NCSC twice. So, well, that is all about Ankur. And Ankur, I think you are free to begin today's session.
Yeah, sure. So, hello everyone, and as Sautik has already introduced me, I'm Ankur Mishra, from a changemaker at Department of Astronomy and Astrophysics at Spaceonova. And is my screen clearly visible to all of you,
Yes,
Sautik?
yes, Ankur, it's perfectly visible.
Okay, fine. So, as Sautik told you, that today's session will be concerned more with the theoretical aspects of astronomy as well as some applications of it using Python. So, we will study some of the concepts and then we will apply Python to the data available to get some very interesting results out of, you can say, the telescope data that we have. So, today's session is going to be much more interesting. No shade, Sautik, but yes, for the astronomy enthusiasts, it would be. So, before we begin, I would like to ask all of you a question, and you can answer it in the chat box, uh, which is, what is astronomy? What is the first thing that comes to your mind when you think about the word astronomy? It may be a picture or it may be a word, anything. Just write the word that comes to your mind in the chat box.
So, guys, whatever you think or whatever comes to your mind when you're writing astronomy, just go ahead and mention in the chat section. And today we have a small audience compared to the previous day, but I think all of us would be space enthusiasts. So let's see, what do you have in your mind, or what do you think? What is astronomy? Just try to say the word or phrase. I think that would be it. And for the people who are joining just now, we are asking you, what is the first thing which comes to your mind when you hear the word astronomy? So I have a few answers, which is study of space with a scientific approach, the science about celestial bodies, planets, etc. Study of everything in the universe beyond Earth's atmosphere. All right, all right. I mean, yeah. So those are the two, three things. Basically, everyone is saying it's a study or a science of celestial bodies and anything beyond Earth's atmosphere, or the study of space in general. SJ, the official gamer, is saying that it's sun and moon. Okay, and we are the unofficial gamers. He is the official gamer. So the gamer says it's sun and moon when you're the word astronomy.
So, actually, it is pretty much everything what astronomy is about. It is the study of all the celestial objects. But in addition to that, you can say it is the study of all the celestial phenomena. Like, for example, you can say the study of space supernova also comes under the field of astronomy. So, the study of all the celestial bodies, all the phenomena that is happening in the cosmos is astronomy. So, as you might think, astronomy is not a very narrow subject. It is a very broad subject. We cannot study astronomy as a whole to a complete detail. If we want to study astronomy to a better extent, we need to divide astronomy into its subtypes so that we can clearly study each and every aspect of it. So, this is exactly our next topic, which is the types of astronomy. So, uh, types of astronomy can be we can have various types of astronomy based on various factors. There is no such fixed classification of astronomy, but here we have focused on classifying astronomy based on the work done in the particular field that we are looking at. So for example, the first one is radio astronomy. So radio astronomy, in the radio astronomy, we collect the data that comes in the radio waves region and we store it. So we collect it using some radio observatories and then we store it in the form that we'll see in a few minutes. So this branch is known as radio astronomy, in which we store the data in that comes in radio waves. So many exotic objects, for example, quasars may emit in radio waves. So radio waves are, you can say, a very good way to study about the cosmos, because they are not the thing that we can easily see. We cannot see radio waves. We can see only in the optical region. So studying any electromagnetic wave that comes that lies outside the visible range, you can say it's some extra information that we cannot get while looking at the cosmos. So this is radio astronomy. The second one is optical astronomy. Now optical astronomy is quite a similar branch in which we collect and store the data that comes under the optical region. So everything that we can see through the telescope such as Hubble comes under optical astronomy. So these two, along with various other fields such as the X-ray astronomy, constitute the observational astronomy. So observational astronomy, the aim of observational astronomer is to collect the data and to store it for further analysis and you can say drawing out results from the data. So this basically is the observational astronomy. Then we have our third field, which is the theoretical astronomy. And theoretical astronomy is quite different from observational, because in this we analyze the data. We don't directly go to the telescopes to collect the data in theoretical astronomy. We analyze the data and draw conclusions out of it. So for example, if we have a Hubble image, say, which we collect through optical astronomy, then we will process the image, analyze it, and draw conclusions out of the data that we get. With all these things comes under the theoretical astronomy as part. So all the cool theories about the cosmos, all the, you can say, interpretations and postulates that you see every day on Instagram or on YouTube comes from the this area of theoretical astronomy. So theoretical astronomy does not mean that we only do it on pen and paper and we read books in it. We actually we extensively use computers in theoretical astronomy, because the data that we collect today, the size of data that is collected today is not so small that we can easily do it on our own. So we use computers to help us analyze the data. Now we have the fourth part of astronomy, which is computational astronomy. So computational astronomy, although the name may confuse you, but computational astronomy is quite different from theoretical astronomy. This is majorly concerned with the simulation of objects and phenomena. So for example, what is a simulation? I have an example for a simulation, which is this. So here you can see a very beautiful merger of two galaxies, which, as you can see over here, there is a time scale which runs over billions of years. So there is a beautiful simulation of galaxies merging together, which happens over billions of years. So you know that human lifespan is not as large that we can stay and see the whole merger. So for seeing the merger, we need to do something that we can simulate the exact same process without actually seeing it. So this exactly is exactly what the computer simulation does. So computer simulation, we put in the initial conditions, such as let's say the conditions, the velocity and the position, let's say, of the galaxy, and then the computer simulates it for us, and we can see the whole range of the time scale that happens. Like for example, if we give the initial conditions at 3 billion years, we can see the whole range of phenomena that happens from 3 billion to 5 billion years by simulating it on computer. So this is computational astronomy and simulations. So for an easier example, I'll show you an image, which is this. So this image is quite familiar to me, and I would like to ask you all, you can write in the chat, what is this object, which movie is it from, and if you can remember what's its name.
Well, I have the name of the object, which is black hole, black hole, black hole. Then black hole again. And the examiner is writing interstellar event horizon. All right, interstellar event horizon and black hole, black hole, black hole. So those are the only answers which I have currently.
Okay, so sure, this is a black hole, and we can also see the event horizon of black hole in this, but this is not only the event horizon, it is the whole black hole. So this is the black hole from the movie Interstellar, which was named Gargantua, the massive black hole. So this was a simulation that was made back in 2013. And the interesting fact about it is that this simulation was quite mathematically correct. So it was not very random and just a, you can say, uh, any simulation of a black hole. It was quite mathematically correct, and it was done by scientists. So this was a simulation that was made back in 2013. Is the point what I'm trying to emphasize. And this one is the image of a black hole that was taken in 2018 and then rectified in 2020 with some magnetic fields. But the point is, compare these two images. The first image is much more clear and gives every proper detail of a black hole that we need, while the second one is quite blur. We cannot even figure out where exactly the black hole boundaries lie, and yes, it is not very clear, and we cannot extract much data out of this black hole image. So this is the difference between a simulation and an original image. So you can say that we can simulate things that we may not be able to observe physically in, you can say, 50 or 100 years. So for example, these images are separated by around 10 years, but the quality of first one is way better than the second one. So this is the power of computers in the field of astronomy. That's why we need computers, and that's why simulations are very necessary, because physical data may not always make sense to us, and may not always provide all the details that we need. So moving on, we have some special libraries in Python that are very special for that is meant for this very special branch of science, which is astronomy. So the first and the foremost library that we'll be using the most is Astropy. Now, Astropy is a library that was made by astronomers and for the astronomers. So Astropy basically has all the functionalities that an astronomer needs in his or her daily life. So it has all the functions, all the constants, and basically everything. So Astropy is very convenient also. We can easily use it, easily learn to use it on Python. But there are some functionalities that are better in some other libraries. For example, the differential equations and you can say the mathematical equations of SciPy. They are way more easier to solve in them compared to AstroPy. So we use SciPy for that. Then we have NumPy. So all the data that I've been talking about is is stored in the form of arrays. Now NumPy, you might have learned yesterday, it is the manipulation of arrays made very easy compared to the regular Python manipulation. So NumPy is the best tool to manipulate arrays, you can say. So it is the best tool to manipulate the data. So that's why we need NumPy. Similarly, we need pandas, because pandas is quite helpful in the big data analysis, especially. So and here we deal with a very enormous data. So pandas is a must for doing the astronomical interpretations. Again, we have Matplotlib. Now, the library still now has all the mathematical and physical functionalities, but Matplotlib is quite different from them because it helps us to visualize the data. For example, I have the data in form of an array or a table. Now, I want to plot a graph of it, or for example, if I have a pixel value, a table of pixel value, and I want to plot an image out of it. So, what helps me here is Matplotlib. Similarly, we have Seaborn, which has the same functionality as Matplotlib. Both of these are used for data visualization, but Matplotlib is quite flexible compared to Seaborn, and thus we will prefer Matplotlib over Seaborn. Now, I have been talking about data since the starting of this session, and I told you that it's array, but it's not any kind of array. It's especially the flexible image transport system. Now, flexible image transport system, or the FITS files. The FITS files is the best way to store astronomical data. It's flexible because you can store anything in this type of file format. You can store, let's say, a book in it. So, flexible image transport system looks like this, you can say. So this is a GIF that is made by stacking images one over the other. So an image is a 2D FITS file, and if we stack images one over the other, we have a GIF or a video. So this is a stacking of several FITS files. Now the basic aim of FITS file is to store, transmit, and process data. Now the storage is very easy, as I said, because you can store the data along with the details that accompany the data, the details that are necessary to know what the data is talking to, what the data is saying to us. So transmission of data is very easy because it's easily you can say we can easily transport this system from one system to the other, and we can use it on different systems easily. Now processing is easy because it is in the form of arrays, and as I told you, arrays are very easy to manipulate in Python. uh, Now I have an image for you. These are you can say these four different fits files, an image of a galaxy taken from different filters. Now what are filters? So when we observe something from the telescope, we can put a filter over it. Now filter is a colored glass or some material, a colored material that that allows one wavelength to go inside, and the rest all wavelengths reflects from it. For example, the blue filter allows the blue wavelength to go pass through it. Well, similarly, the red one allows red light to pass through it and reflects all the others. So we have three filters over here: the blue one, the red one, the green one. But we have another mustard colored filter which makes no sense to us at the point, because as I said that we have three filters that can make any color in the universe. These three filters, you might know that red, blue and green are the basic colors of the universe. You can add them in different proportions to make up any color in the universe. So what's the use of this mustard filter? So for example, just for instance, let's say you take up your mobile phone and you capture the image of the sun at noon. So at that time the color of sun is very close to white, and it almost merges with the background sky. So you cannot clearly tell me where the boundary of the sun lies. So it is quite difficult to observe it. So similarly, we have moon with the same angular diameter, although it shines quite brightly. But if you take the image of a moon at suitable time, you can easily figure out the boundary of moon and separate it from the neighborhood sky. So the point here is the sun is far more brighter than moon, and in the fainter images or in the dimmer images, we can make the finer details very clearly compared to the brighter images. So this mustard color filter cuts off some light that and doesn't allow the light to pass through it, and hence when we stack the images one over the other, we we kind of get an image with less intensity, and so we can see all the finer details of it. So as you can see, when we stack these four images one over the other, we get this final image which represent the original image of the galaxy. So this was the first part of the theoretical aspect. Now I'll hand it over to Sautik for taking us to the world of Python. Sautik, over to you.
Thank you so much, Ankur, for the wonderful introduction about what is FITs and how do they really work. And I believe that I already have a question in the chat by Swapnil. Swapnil is asking, are these libraries professionally used too, or do NASA and ISRO use some non-public ones?
Well, NASA, I'm not very sure, but I think NASA and ISRO, when they use Python, they have to use these libraries, but usually they have their own systems for interpreting data. They may use some other languages also. So yes, if they use Python, they have to use these libraries at some point or the other.
Right, so I hope that Swapnil, your query has been answered. And with this, we can now begin to the Python part. All right, so let me just go ahead and present my screen. Give me a moment. Right, so just give me one moment. I'll just present my screen. Right. Circle is on screen visible.
Yes, I think it is.
Okay, fantastic. Okay. All right. So everyone, welcome to this week's applications part. And the very beginning, as I'm going to explain a lot about this, we see how you can open up its image, you can load the data, and you can display the data. So those are basic things which will be seeing now. If you do that, what I have done is that I have to use another module for that particular purpose. And that module is named as Astropy. This module may or may not be your system. So what we will do is that we will first go ahead and install Astropy on our systems. To, to install Astropy, what you can do is you can just first simply go ahead to whatever your private notebook is, then click on the new button and then click on the terminal button. Once you do that, a terminal would be prompted, and it is, I'm using Windows, so showing is Windows PowerShell. If whatever you are using, it will be showing right over here. Once the terminal has been loaded, enter the command pip install Astropy. And this command installs Astropy on your system from the internet. It goes ahead and installs Astropy on your system. And if you see, this Astropy module also means Numpy module. So in case Numpy is also not installed on your system, it will install Numpy as well. So Astropy comes with Numpy as well. Okay, so with this command, with this pip install Astropy, your module would be installed on your system. Once the installation is complete, you are free to use. So we'll be using some visualization modules, not that important. Then I will be using something known as a Matplotlib. So I'm doing import matplotlib.pyplot as PLT, and this module we should be using for plotting purposes a lot, and it's the most used module. Then I'll be also importing NumPy as a key, which we have already seen in the previous session. So we'll be using NumPy as well. And then the most important one, that is from astropy.io imports fits. And this is the one which we would be dealing with. Okay, this is the one which we'll be dealing with. And this module, fits module, is what we will learn in depth about. So let's open up its file to see what it contains. To do that, I'll be just simply using fits.open. If I do fits.open, this also.fits file, whatever was there on my system, gets opened and loaded into the variable. And then if I do .info, I can see that there are two lines. What are these two lines? Well, these two lines are something which Ankur would love to throw light on. Ankur, can you explain a bit about what are these?
Yes, sure, Satvik. So, as I already vaguely mentioned while explaining it, the FITS file contains both the data and the description of the data. So here HDO is the header data unit, which you can think about as the building blocks of the FITS file. So each header data unit contains a header uh, and the data. So the data is the main thing that we are trying to analyze. For example, here it is the pixel values. So the data is in the form of array. Now we have the header that has all the necessary information, although it is not the mathematical data that we're looking for. But for example, the header may contain all the, let's say, the date and time of collection, the telescope from which it was collected, and all the astrometry data, etc. So header, you can say, describes the data, and HDO consists of the building block of the whole FITS file. And here we are only concerned with the primary HDO and not the second one.
Correct. And just like Ankur already said that in every HDU, we have two components, a header and data. So let's first do of 0, and then we'll first see the dot header. And this is where you see a lot of information. A lot of information starting with your x-axis, I mean number of pixels on the x, the y, the date, the origin, the survey, the region, the satellite, the telescope. You have the longitude, you have the latitude, you have what instrument they're using, you have so many things. And for people who are into astronomy, it is like jackpot for them. There are so many coefficients, as you can see. There are coefficients, and it's just a lot of information which is there in dot header. If you do dot data, you get the main data, which is a two-dimensional array, or that is your image. Now, what we'll be doing is that once your data has been, or this is the data which we need. First, let me just go ahead and undo all this. And there you go. You have the header and you have the data. So this is the final data. But you tell me that sort of this is a lengthy process because first you need to do dot open and then you need to do of zero dot data to storage into variable image data, and that's a long process. Is there a shorter method? I'm like, yeah, there is a shorter method, and that is just fits.get data. And that is just one line of code, fits.get data. And with that, you can again get the entire two-dimensional array much more easily this time. Okay, much more easily this time, and not using all the different things. All right. now, now that you have your image, it's time to plot the image. Okay, it's trying to plot the image. And now to plot the image, what we'll be using plt.imshow, or which is known as plt.image_show. And then you'll pass in your entire two-dimensional array. And I'm using a color map of gray. Make sure that the image is looking black and white. And there you go. That is the image which we are looking at. That is the image which we're looking at, and that is a beautiful image of our Orsed network. So that is how you can see what is there in the pixel image. You could also get some basic statistics of the image, that is the minimum pixel, the maximum pixel, the mean, and the standard deviation. Now, if you see carefully over here, that is the mean. Okay, the mean of the image is just 3,759, and the maximum is 23,000. All right, and the mean is just 9,800. So I believe that the overall, okay, the overall is much more inclined towards the mean, and that is why, this image looks a little bit off, looks like a little bit darker. Okay, not okay. So that is fine enough. But let's try to see, or let's try to plot the histogram. Now, for plotting a histogram, we'll be using plt.hist, which stands for histogram, or matplotlib.pyplot.hist, which stands for histogram. For plotting a histogram, we need a one-dimensional array, so we need to convert this entire two-dimensional array into a one-dimensional array. For the conversion, we'll be using dot flatten. For the conversion, we're using dot flatten to make, or to flat the entire two-dimensional array to become a one-dimensional array. Now that we have the one-dimensional array, we can plot in our histogram. Once we plot in our histogram, we see this is the wonderful plot which we see. And yeah, right here. This is the plot which we are seeing right over here. And there are a few things in this particular image, or in this particular histogram which we can understand from. At the very first, if you see the maximum intensity of these pixels at around 7,500. Okay, at 7,500 as the maximum intensity of pixels, which is contributed by the pixels on the left hand side. If you see, most of them are in the black region, and that is what contributes the first peak of the image. Then the second peak is somewhere around 12,500. Okay, it's at 12,500, and that is contributed by these lighter pixels. If you see on the right hand side, that is what contributes towards the second peak. Now, the third thing is that all the values more than 20,000, More than 20,000 is just a few of these pixels, and these pixels are nothing but my stars. Stars do not occupy much space, they don't occupy much pixels, and that is why they are less in number, and they're represented by these small values which are greater than 20,000. That is what you mainly consider it to be the stars region. That is what the entire two-dimensional or this entire histogram represents. Okay, that is fantastic. But now, as I said, that the image was a bit darker, so I did something and I converted the scale from a linear scale, which is 5, 7, 10, 12, 15. I converted into a logarithmic scale, which is like 4,000, 6,000, 10,000, 20,000. So for that, I have just changed the colors. That is it. So that is why I'm importing log node from Matplotlib dot colors. Okay, Matplotlib colors and put log node, and then I change the color scale from linear to a logarithmic scale. And if I do that, I see some difference. I see a difference between this image and that image. Can anyone of you tell me what's the difference between that image and that image? Anyone? Just mention them in the chat section. What is the difference between this image and that image? Let me have a look at the chat section. Let me see. Okay, Uncle, what do we have in the chat?
So I have some responses, which is darker. The first one is darker. Then someone says it is the contrast between them.
Mm-hmm.
We also have some scale difference coming in.
Yeah.
The color scales, yes, yet again.
Mm-hmm. Well, yes, you are right. The color scale is different. And because of the difference in the color scale, the image appears to be brighter, or you can say more contrast and all the things associated. Now, I'd like to show you what is the major difference in the scale. So let's see. Let's consider a value 10,000. Okay, this 10,000 is somewhere around this range. Which is this range? This range is around the 600. Okay, so somewhere around the 600. So it is there over here. 10,000 values represented, or it is somewhere along the lines of 600. The same 10,000 value is somewhere around the lines of 400. So do you see that 10,000, which was first over here, has now shifted over here? And because of that, the color has changed a lot. 10,000, which is supposed to be here, making it all darker, has changed and now it's all little lighter. Similarly, I can say the same thing for all the different pixels. 6,000 wasn't definitely over here, it should be over here or something, but now 6,000 has increased. Similarly, and 20,000 is right there on top. And because of that, the image looks a little bit brighter. And yes, it is brighter because I've changed the color scheme. You'll get a more you get a more better visualization if I just go ahead and change the color map from gray to magma. See how beautiful this image looks? And I just go ahead and do the same thing over here as well. Let me just change the scale to magma. Now, as you see over here, one side we have very purplish or violet, and the right hand side is all orange. Okay, and over here on the left hand side it's more violet, and the right hand side is more purple. Orange is just over here. It's just a little tint of orange over here, a little pinch of orange. But over here, the orange contributes the right hand side completely. So I think this would now give you a more better idea of the color scale or the color bar. 10,000, which over here was here, therefore it was first all purplish, now it has become all orangish. Okay, so I think that would now help you understand it further. Now you'll ask me to stop it. Where do you get this horseshit outfits and all the outfits by? So I got this from an server, which is your HDSS data archive server, which we use in DR12 SDSS. Okay, using DR12 SDSS archive server, and over there I'll be searching for an object name. Let's say I'm searching for Right, M42. Let's go ahead and submit it. And there you go. That is your M42 image which we have just received. Now I will download the ultraviolet band, the green band, and the infrared band. So I'll be downloading these three bands on my system. And once these three bands are downloaded, I can simply open it using fits.open. And again, I'm doing dot header to first show what is the entire header. Again, a lot of information, but this time we have we should have, yeah, there you go. So this is my RA, and that is my check. And then you have your telescope tab. There you go. So you have a telescope, which is a 2.5-meter telescope. Then you have the rate of observation, and so on and so forth. All right. So you have all these observations, which you saw using dot head. Now you want to plot it. I'm now shortening things. I'm just plotting it using a single statement. That is plt.im show, which is greater image show. I'm using the fits.get data to get my data, using my log norm, and using my color map as blue. If I do all these things, there you go. That is our image which we receive. And that is a beautiful image as the same M42 under ultraviolet. Then you have M43, M42 under your green filter, and this is your M42 under your infrared filter. But wait a minute, I see there is some difference between this image, that image, and that image. I mean, I know the colors are different, that is blue, the green, and the red, but other than that, there are some more differences as well in these three images. Can one of you tell me that what is the difference between this particular image and this particular image and this particular image? Anyone? You just mention in the chat what is the difference between all these three images apart from the colors. Apart from the colors, what are the differences which you are seeing currently?
Okay, so we have some answers. The first one is the dark patches or dark spots. Someone says it is one of them is more uneven. Someone says the spots are more visible in red than blue. And yes, again the same. Red has more dark points compared to the blue one.
All right, so everyone is saying dark points, spots. Okay, but what are those spots? 10 million points to whoever answers it correctly. What are those spots? There should be something, right? I mean, yeah. So what are those spots? Anyone?
Okay, so someone has answered stars. Yes, two of them have answered stars.
Exactly. That is our stars. But why are they so much? Why are they more in my red compared to my blue? Well, the answer is with Ankur. And Ankur, could you reveal the answer?
Yes, sure, Satik. So yes, the dark spots are more in red one, and yes, they are stars. So the reason is the blue one, as we said, is the data that is collected in the ultraviolet region. Now we know that ultraviolet light has a much smaller wavelength when compared to the red light. So and we know that nebula is made up of all the dust and particles that may scatter the light coming through them. So these stars are situated behind the nebula as seen from the Earth. So when the light, which is a mixture of all the possible wavelengths, which when it crosses the nebula, the ultraviolet light gets scattered in the nebula more than the red ones. So this is quite similar to the fact that the sky appears to be blue and it appears red only during the sunset and sunrise. So this is quite similar, and the blue light coming from the stars gets scattered. Only the very energetic radiations reaches. So This is not true for the red light because very less red light gets scattered compared to the ultraviolet, and thus we can see more number of stars in the red region when compared to the ultraviolet region. So this was the basic reason behind the difference.
Right. So that is why you see this difference between all these three images. And well, seeing all this and seeing everything just makes, I mean, I'm just completely shocked. And yeah, that is my reaction right now to respond to all these different things which we are seeing right now. Okay. So, all right. So now we can stop for a few moments to answer any questions if you guys have any. So please mention your questions in the chat section and we shall be taking each and every one of them. So guys, if you have any questions, please mention them in the chat section and we shall take up them one by one. All right. So just go ahead and mention them in the chat. All right. So let's see, do we have anything in the chat section? Yes, we have. How does it? Okay, so Swapnil is asking a lot of questions. So, how was the data set loaded? Please elaborate more about the FITS file format. Okay, Swapnil, for the loading of data, we just used fits.get data and we got a two-dimensional NumPy matrix, or you can say a two-dimensional NumPy array. That is how we got the entire data, which was stored in the FITS image. Then please elaborate more about the FITS file format. Ankur, I think you can go a bit about the FITS file format.
Okay, so sure, Satik. So FITS file is basically a file type that stores data in the form of several units named as the header data unit. Now, header data unit, each header data unit has a header which describes the what the data is about and several specifications about the data. And then we have data which just stores numbers or characters in the form of an array. So you have also asked that how these these numbers represent image. So basically, these numbers are the pixel values corresponding to each and every pixel of these images. So we assign a pixel a particular value according to which it changes its colors, its color to the required proportion of red, blue, and green. So this is all the FITS file is about. So it can store any kind of data. It just stores numbers in the form of arrays.
Right. All right. So again, Swapna is asking that how does it store images but displaying dotting issues numbers? Okay. So Swapna, it's I mean, that is the what you can say. That's reality of a FITS file. You can store anything, whatever you want. It's just that dot info shows numbers. I mean, it does not show numbers technically. It just shows the two header. I mean, for now, we only have two HDUs. If you have more HDUs, we have like three, four, five HDUs. Then we would see all the different HDUs over here as well. Okay, so we can have that, or we can see that over here. But that is what the dot info says. It says what are the different HDUs available, and then it tells what is or how or what all does every header data unit stores. Okay. So yeah, so that would be it to about your different header data units. All right. So, do we have any more questions? Let me have a look. Do we have any more questions in the chat section? I guess no. Does anyone else have any question in the chat section?
Not actually. Sorry.
Okay, perfect. All right. So now we can begin to the second half of today's session. So, Ankur, I think you want to go ahead and present your screen.
Yes. So is my screen visible?
Yes, it is visible.
Okay. So we will begin with the second part of this session, and it will again start with a question as usual. What is a pulsar? Now, whatever comes to your mind first, you can write in the chat. What is a pulsar? Uh, you can write the description, or you can write just the words that come to your mind. Anything.
And within a few seconds, we already have a response which is rotating neutron stars. There's one response which I got that is rotating neutron stars. Then because the only response which I have received is just rotating neutron stars, and I think that is a rotating neutron stars which is highly magnetized. Okay, so two responses: rotating neutron stars and rotating neutron stars which are highly magnetized. So I think our audience is not aware of the word pulsar, and maybe I think
Yes.
we can go ahead with reading the answer.
Yes.
The,
So
that is
this
the
is
pulsar,
the pulsar.
and you guys can even guess it. Sad. Again, your jokes apart, I mean that's not the real
Yes.
pulsar. Okay, so move ahead, and this is one is real pulsar. Okay.
And you correctly said that it is rotating. It's not exactly a star, but yes, it's a remnant of a star. And someone said that it is highly magnetized neutron star. Yes, it is highly magnetized neutron star. That's perfectly correct. Now, this is also very energetic, and it has a very rich, you can say, particle medium surrounding it, which consists of electrons and other imaginary particles. So, the very high magnetic fields that come out of these poles of this uh, neutron star or the pulsar channelize the electrons around it and inside it. So these electrons, when they get channelized, they radiate energy. Like anything which rotates loses energy at particular time. So it also loses energy to radiate. Now, the energy is so high that the radiation, the photons, are built up in the region of X-rays. So we can see X-rays coming out of the poles as these conical beams in the GIF. So these are the X-ray radiations that come out of the pulsar due to the channelization of electrons. Now, there are several specific or interesting facts about pulsar, that it is the remnant of a star, as I said. What this means is a pulsar is formed when a massive star, which is massive enough to undergo supernova but not massive enough to form a black hole, when it undergoes supernova, the star forms a neutron star. Now, the neutron star with a very high energy comes into the category of pulsars. Again, the pulsars, or in general neutron stars, are so small in size that it is uh, actually impossible to see them physically or optically. So we cannot observe a neutron star under a telescope, because the diameter of a neutron star is around 20 kilometers. Now, you can imagine the crazy density of these neutron stars, because the size, as you see, is only 20 kilometers in diameter, and the weight may vary from 2 to 3 solar masses. So this is quite uh, dense, and you can compare the density of a neutron star to that of an atom's nucleus. So these are some facts about neutron star. Now, moving ahead, it also has a particular feature known as the periodicity of the neutron star. Now, due to this periodicity function or feature, it is compared to the lighthouse. Now, lighthouses rotate about one of its axis. so that the light reach 360 degrees around them, and thus the ships, when they receive light, they can navigate to the lighthouse. So similarly, the X-rays are coming out of the poles of these neutron star, but it rotates about some other axis other than the poles. So it the beam does not point towards us at all the times. It points towards us only at specific instances of time. So, for example, you can see that the beam is rotating, and it when it points towards us, let's say that we take that time as t equals to 0. Then after, let's say, a time capital T, it again points towards us. Then we can be sure that it will point again towards us after the time capital T is elapsed. So this is the periodicity, or the regular nature of the X-ray beams from pulsar pointing towards us. So this is the periodicity feature of pulsar, which is very helpful when we separate the data from noise. So we will see the how we separate the data and what is noise. So before that, I want to show you two cases of a detection of a pulsar. So these are the images taken at very small interval of time. So one of them, you can see there is a red circle and there is a dot inside it. And in the second one, we have the image of the same region in the space, the same field of view, but that red circle and the dot inside it is absent. So what happens is, in the first instance the pulsar is pointing towards us, while in the second one it is not. So based on only one image, we cannot judge whether a pulsar is present there or not, because it may be misleading. Because as you know, that pulsar does not point towards us at all the times. It points towards us at an interval of specific at a specific interval of time. So we must have several data points or several images to conclude that whether a pulsar is present or not. So we stack images one over the other to conclude that. So you might also see that there are several other points over here which are absent, and in a sense, these two images does not seem like they're from the same field of view, right? These are quite different. But the other sources are not the sources of interest. Those are uh, the noise sources. Now, noise can be generated by any phenomena, like the X-ray is generated when one of the five basic generation phenomena of X-ray happen. So there may be some of these phenomena happening around in the nebulas or etc. So what happens is, the point sources that are not pulsars, they also emit in X-ray. Now these X-ray contaminate the data that comes from the pulsar. So we cannot pinpoint whether a point source emitting X-ray is a pulsar or it is a noise. So for that, we have several other detection techniques or analysis techniques that helps us to conclude whether a pulsar is present or not. So for that, we see this Gaussian distribution. So this is a beautiful Gaussian distribution with no, you can say, no disturbances to it. The x equal to 0 coordinate correspond to the point where the pulsar is present. We can treat it as a point source because it is very small in size. Now this x equal to 0 coordinate correspond to the point where pulsar is present. Now we have a very high amplitude of X-ray, that corresponds to 1.0 in the graph. So only at the point x equal to 0 and some points surrounding to it, we have some finite amplitude of X-ray coming in. While this is the ideal case, what we get in reality is this second image, this mess. Now you cannot conclude whether there is a pulsar present or whether there are discrete X-ray sources or there's a continuous X-ray source or anything. You cannot conclude anything out of it because it is just full of noise. You cannot see the original data that comes in. So this is because, as I told you, that there may be some other physical processes that may be going on in the surrounding of the pulsar, which contaminate the data. Now these are the noise sources, and what we do is we eliminate the noise using some method that I'll tell you, and Sotik will do it physically on Python notebook. So what we basically do is known as the we increase the signal to noise ratio. We increase the, you can say, the intensity of signal to the ratio of intensity of signal to the intensity of the noise. Now, here we have some amplitude of X-ray coming in, which may be because of any type of X-ray sources. Now, what happens? What is special about noises is they are physical processes, and all the physical processes uh, that comes under the regime of quantum mechanics follow the probability distribution. So what this means is, suppose I have a physical process that generates a X-ray of amplitude plus 5. Then I have equal probability that at other instance of time, I will have a physical process that will generate the amplitude of minus 5. So the noise is random and probabilistic, so we can easily add the images, add the pixel value or add the intensity values of the images, so that we can cancel out the plus 5 and the minus 5, for example. So we get only the data that comes out of the pulsar. Now pulsar is periodic and it is not random, and thus we cannot say that the data from pulsar cancels out. So only the noise cancels out and we are left with the real data that we are interested in. So when we do this, we get this fourth image. So although it is not fully free of noise, because we are only dealing with the probabilistic case, but it is much better than the second one. And we can see the peak of the Gaussian distribution. We can see that there is something that is generating periodic X-ray, and when we average this data out, we get a proper Gaussian distribution, which is very easy to analyze. So this was all from the theoretical side, and now we'll go on to do some Python simulations and analysis, obviously. Over to you, Swati.
Oh, well, thank you so much, Uncle, for the lovely explanation and the cute image that you see. Let's just go ahead and screen. Uncle, you can open it. Right, and let's go. All right. Is my screen visible, Uncle?
Yes, Swati, it is.
Okay, perfect, perfect. So, all right. So now we'll be finding hidden pulsars. Okay. So what I'm first doing is that the same bunch of modules again, which we are using, just the same bunch of modules, but now we have some difference. The difference is that I have a fold over here, and this fold has 5 images. Okay. And I'm plotting all of them using a for loop that is for I in data. Just doing fits.get data of I. Okay. And I'm just simply iterating through all these 5 images and plotting all these 5. So there you go. This is the first one. And if you see over here, in the first one, you can see the pulsar very clearly visible right in the middle of the image. This is the second image. If you see, again, the pulsar is there and it is visible right there again in the middle. Then if you see the third image, the pulsar is kind of there. Pulsar is kind of there, but not much visible. So it's like, all right, it's fine. The fourth image is just not there at all. Fifth image, again, it's there. So what we see is that out of the 5, 3 of them have pulsar prominent, but 2 of them are not having the pulsar prominently. Okay. So what we'll be doing is that we would be stacking them together. And for stacking, what we are doing is that we are increasing the SNR or the signal to noise ratio. And how am I stacking? People have different ways of stacking. What I'm doing is that I'm taking the first pixel over here, then adding it to the next pixel over here, that is the second, or that is 0 pixel of the second image. Then you have, or I'm adding it to 0 pixel of the third image. Then I'm adding to 0 pixel of the fourth image. Then I'm adding it to 0 pixel of the fifth image. And I'm adding all and then divided it by 5. Okay, I'm dividing it by 5. So out of all of them, I am just taking or just adding and then we divide by 5. How am I doing that? Well, I'll be using a similar approach, which I've done in the previous session as well. I'll be taking all these different arrays and adding out of or just contacting or just appending them into one single array. Okay, so I'm just contracting them into one single image. And once that has been done, I'll be just doing np.mean axis is equal to 0. Remember, which we did in the previous session? Right, it's the same. We'll be using the same case over here. All right, So now once that is done, once my stacking and everything is done, now I'm simply plotting my image. And how do I plot this kind of image? Well, very simple. I just simply did np.mean and I'm doing plt. I am sure the stack mean. That is it. That is a stacked. That is a stacked image, and you can see the pulsar very clearly visible. Okay, you see the pulsar very clearly visible, and well, that is it. Okay, and that is how you just plotted, and you just plotted or you just stacked an image using Python. Once the stacking is done, let's see the histogram. This is the histogram of which I'm plotting of a random image. Again, I'm using the dot pattern and everything. This is the histogram of a random image, kind of alright. And this is the histogram of the stack image. Now, if you see over here, uh, 1 second. Ankur, is my voice shit audible?
Yes, Otik, it is.
Okay, perfect. I think I'm having some internet issues, so just let me know. All right. So this is the histogram, or that is the histogram of the two. And yeah, there's not much difference between these two histograms. It's just that this is my hair when I wake up, and this is my hair after I've combed. So that is the only difference which I can see in these two histograms. Okay, not that much better. Okay, so what we thought is that okay, so mean is one method. Do we have another method? And like, yeah, we have. So let's consider an array which has like 1, 2, 3, 4, 5. And the mean and the median of this complete array is just 3. Okay, it's 3. It's 1, 2, 3, 4, 5. The mean and the median remains 3. But let's say that there was noise, and instead of 5, we have now 50. Okay, instead of 5, we now have 50. Now, what happens if I do the mean and the median? Well, the mean shifts. The mean shifts towards the higher or tries to accommodate all the different values, and the mean has shifted from an original of 3 to now 12, and the median remains the same. Okay, because it's a central tendency, so it remains the same, but the mean has shifted a lot. Mean has shifted a lot because it was trying to accommodate the noises as well. The mean does not know that it's a noise. So we decided that, okay, how about we do the median method as well? So for median method, I now have 1, 2, 3, 4, 5, 6, and I can add like about 10 and 10 of these images. And I'm again using the same thing, creating a simple list and then doing dot append, which is append in all of these lists. And once the appending has been completed, I'm then doing np.median to get the final median. And if you see, if I'm doing np.median, this is the final two-dimensional array. So let's try to plot it. I'm plotting both the median and the mean as well. So this is my median and this is my mean. Again, I see no difference at all. It almost remains the same. It's almost remains the same. Let's see the histogram. This is the histogram of a median. This is the histogram of the mean, and this is the histogram of a random image. Okay, if you see in the random image, there's so much noise, and it's not uniformly distributed. The left hand side has more noise than the right hand side. Okay, if you see over there, but the mean and the median did a fantastic job in increasing the SNR from this particular thing to just this. It did a particular job, but the mean and the median almost remains the same. I mean, we don't know what is better. Is mean better or the median better? So we don't know what is the better out of two is the mean and the median. So why don't you all take a guess? Which method is a better method? If you think the mean is better, just write mean. And if you're thinking it's median, then write median. Okay? Just write uh, what do you think should be a better method? Is it the mean or the median? Let me know which is the better one. And Ankur, let me know that what is
Okay, so uh, as of now, we have only two responses. Both of them are mean.
oh, both of them are mean. All right. Okay.
Someone says, I hope it's mean.
I hope it's been okay. No problem.
Okay, and he has given an explanation in the favor of mean that it may have a better precision.
So I think everyone is saying it's me, it's me. So okay,
Yes.
so let's see what is the correct one. And to do that, I'll be using 1,000 fits images. How many? 1,000 fits image is what I am choosing. Okay. Yes, Swapnil, we would be sharing you the code and the fits at the end of the session. Don't worry about that. We'll be sharing it with. So this is the 1,000 images. And how am I going to do that? Again, the same thing for I in the range of that. Then I'm using this method. This is a shorthand method on a trick because I have images in the format of 0000, 0001, 0002, 0003, and so on and so forth. So, so I have your yeah. So I have different different names such as 0000, 0001, 0002. So I have of length 4, and that is why I'm appending zeros in the very beginning to make sure they're of length 4. If let's say that I is 100, so it will just add 1 0. If my I is 10, it will add 2 zeros on the left hand side. This is just padding. For padding purposes, we are using this, so no need to worry about that. This is just for padding purposes. All right. All right. This is just for padding purposes which we are using. Now I'll be using your np.mean and np.median as well over here with axis equal to 0. Once I have done, now it's time for the reveal. So this is the random image which you see over here. This is the random image which I'm plotting. Okay, kind of good. Did a good job. Not bad. This is a random image which I'm not supposed or I'm not expecting an pulsar over here. Then you have the mean again. Mean, there is no pulsar over here. There is no pulsar over here. So what if we have the median? Ah, there you go. So that is a pulsar right in the middle, very cute. And as you can see, the highest is just 0.03. And over here, it is going up with 0.2. A random image goes to 1 or 1.5. So that's too much. So because of how feeble the pulsar is, it gets lost in this. It gets lost in this. So 0.03 is just who you and somewhere or the other it just gets lost because all these pixels and all these noise cannot even see first now. Let's see the histogram. This is the histogram of a single image, histogram of the mean, and the histogram of the median. You see how sleek both the mean and the median is. I mean, ideally, it should be a single line, but yeah, the mean and the median did a fantastic job. But in this case, the median did a far better job than the median because of the number of images being 1,000, and hardly a few of them would have our, a few of them which have our pulsar. Okay, so because of that, the median did a fantastic job rather than the median. All right. So yeah. So now we can proceed with the last part of the session. And Ankur, I think you can just go ahead and present the screen. Last part of today's session.
Okay, sure. Okay, so is it visible?
Yes, yes, it is visible.
So, my question is, I'm starting it again with a question, but yes, my question is it over? So, the answer is written here. It's not over yet. As I told you, there are several types of X-ray generation processes, and so there may be several other sources of X-ray. For example, this X-ray binary. See this cool simulation of an X-ray binary, which also emits X-ray, which is quite periodic, but not as periodic as the pulsar. So this is a beautiful intensity curve for this X-ray binary. Again, we have this X-ray transient and the intensity curve for it. So you can analyze it using the same Python techniques. But yes, I would like to study them further, won't you? Now, again, we have astrophysical concept of expanding universe, right? So, from the Big Bang onwards, the universe has been expanding. We have grown from a point to such a massive universe, and it is also accelerating and expanding. So, won't you like to compute the rate of expansion? And won't you like to study the reason behind the expansion? So, if you ask me personally, I would like to do that. Similarly, you can see here this tiny one is the Earth, and these are several exoplanets that we have detected across the Milky Way galaxy. Now, these exoplanets are quite similar to that of Earth. So, what why I'm saying this is there is possibility of life in these planets, but these are so far away that we cannot easily detect life on them. So, won't you like to be the candidate who detects life on them? Won't you like to give it a head start studying these exoplanets? Now, suppose we don't find life on any of them, then won't you like to terraform Mars and habitate it? Like, would you like to go to the Mars? But for that you must transfer your orbit from that of Earth to that of the Mars. So that's the first step that you'll take. So won't you like to give it a head start, like studying how to get from the orbit of Earth to the orbit of Mars? So all I will say is that you can.
We have everything catered and we have everything ready in our Python Space Applications Training Program, which is starting from 24th of January. So it's starting in the 20 days, which is a 1 month long fun ride through Python to the stars. We're having a total of 12 sessions with 10 modules and 2 bonus sessions. So that includes your entire training program. All right, so you'll ask me, okay, Satvik, how much should the training program cost? Well, it costs around 9,000 INR. Oh boy, that's a lot. So that is why we're offering you an early bird offer because it's still 20 days more. And for the early bird offer, we reduced the price from 9,000 to just 3,999 INR for Indians. And for non Indians, we have reduced the price from $130 to just $59 for non Indians. That is for the training program. If you're asking me for the masterclass, well, we also have a masterclass. In the masterclass, we don't have 12 sessions. We only have 10 sessions, and we don't have the bonus sessions, and also we don't have your right. So we also we do not have your problem statements and assignments. So all these things are not there in the masterclass. So that is why the price is from 3,000 INR. We have reduced to just to 1,199 INR. Again, because of the early bird offer for Indians and for non-Indians, we reduce the price of $45 to just $29 for non-Indians. That would be all about the training program and the masterclass. And for more information, you can just visit spaceonova.com/Python. Over there, you'll be seeing all the details which you're looking for. And in that, when you fill out the form, you see you'll get a mail of everything mentioned there in detail. So that is all from our friend, and now we can proceed with Q&A if you guys have any. All right. So now we can proceed with the Q&A. So guys, please mention your queries in the chat section. And before I do that, well, for the resources, you can find us all. You can find all the resources at socketmonday.github.io. So I'm just passing the link in the chat section as well. So right. So oops, my bad. It's a typo over there. It's socketmonday.github.io. Right. There you go. So socketmonday.github.io, and that has all the links which you are currently looking for. Okay. Right. In the four graphs for detecting hidden pulsars, can you explain again how are the noises cancelled out? Okay, so in which four graphs are you saying about? I think you're asking about the the mean and the median, right? So see, what happens is that if you are seeing, or if you are seeing the histogram, wait a minute, I'll just present my screen again. So if you see the histogram over here, this is just a random image over here. Like this is just a random image which we are trying to plot. And how do the
Sotik,
okay, yeah, I think it is about you, Ankit.
Yes, I think it's from the PPT.
Yes, go ahead. Yes, yes, that is the one, Ankur. Right, you can go ahead. Ankur, you're currently on mute if you're saying anything.
Yes, sorry, I started explaining without unmuting. Sorry, I'm so
Yeah,
sorry.
no worries.
So, yes, so in the first one, you can see it is only the ideal case of the pulsar. So the pulsar is emitting at x equal to 0, and since it is a quite a point object, we can estimate that it is only present at a point, and we get the X-ray radiation only at a point. So amplitude is non-zero, ideally only at a single point x equal to 0. But in reality, we have this mess which is made up of the noise as well as the data. Now, as I told you, noise is any other source other than pulsar that is present in the field of view. So for example, just take an example of Compton scattering. So suppose particles in the nebula are undergoing Compton scattering, and thus they are emitting X-ray. So the X-ray from the nebula that may be in the field of view and the X-ray from pulsar cannot be distinguished by the detector because it only detects the presence of X-ray energy. So it reports all the data that comes to it. So the noise from the Compton scattering in the nebula is superposed over the data from the pulsar. So this is called as the noise. Now, Compton scattering, as all the quantum phenomena, is probabilistic. So, for example, at one point, I am getting a positive amplitude of X-ray. Now, at a particular interval of time or at some random instance of time, I will also get a -5 or the negative amplitude of X-ray. So this is because everything in the universe is probabilistic, and you can say the probability of a modulus is always the same. So, for example, the probability of 5 and probability of -5 are the same. So, yes, there's a it is very probabilistic that if we add the images, if we add the intensity value at every point in the field of view, we will cancel out the positive noise with the negative noise. So this is what happens when we increase the signal to noise ratio. So when the noise get cancelled, the intensity due to the signal is dominates over the intensity due to the noise. So this is what happens when we add two images, the positive and the negative noise cancels out. So we get the graph which is very close to the fourth one. So we still have noise because it is only probabilistic, and we cannot make it sure that the noise always get properly cancelled out, but we will get something close to the fourth graph. Now, if we average out the data, we can approximate a Gaussian around this, because you can see a peak over here, which is much better than this second one. So this is what is happening. Hope it's clear now.
So I'm not asking, can you share some more resources to read about this? I mean, to read about pulsars. Definitely, I think we would love to do that. Swapnil. So just connect with us on our LinkedIn, and then we can help you out to read more about or to develop more about these particular fields. Right? So we'll definitely do that. Apart from that, do we have any more questions from anyone? All right. So I think we do not have any more questions. So thank you so much for the wonderful session. Thank you so much for the lovely audience for listening to us patiently. And thank you so much, SOA ACM Chapter, for giving us the opportunity to go ahead and conduct this workshop. And if we are sure, you can go ahead.
Hello everyone once again. I am Priyanshu, Treasurer at SOA ACM Students Chapter. On behalf of our SOA ACM Students Chapter, as well as our College Institute of Technical Education and Research, as well as the entire fraternity of our organization, that is Shiksha Anusandhan University, I would like to thank our guest speakers, that is Sautik Nandi and Ankur Mishra sir, as well as I would like to thank whole team of Spaceonova for briefing us with knowledge of Python, as well as giving us a great idea in the field of space science. As well as I would like to thank our professor, Dr. Manoranjan, Manoranjan Padi sir and Suman Sau sir for guiding us for successful conduction of this event from SOA ACM Students Chapter. As well as I would like to thank our Center for Excellence in Data Science and Google Developer Students Club, and to all the participants for attending this event and maintaining the discipline and having the patience and learning a lot. I hope all of you guys have really enjoyed this session. And here I declare the end of this 2 days Python with space application workshop. Thank you.
Thank you once again.